And let's take a tour. So we were started there, and then we were talking about destruct plate boundaries and all that stuff, size of the plates, earthquakes, seismographic, kinematics, relative versus absolute plate motions, how we determine poles of rotation, you know, and I added this. This is kind of cool. So I showed you this last time, but then I go, oh, they're not showing any geology. So what you can see is, here are the cratons and these areas with little deformation. These are these areas of Archean cratons for the most part. I just thought I'd add that in there. Kind of cool. All right. So we strain map, earthquakes, geology, absolute plate motions. We talked about mantle plumes, Hawaii. We love Hawaii. Going to take our class field trip to Hawaii. We talked about the plume model versus the plate model, about all the hotspots and how we can use the word hotspot to sort of not take up side in that controversy. We talked about predicted hotspot tracks, talked about lips, and we started off with sort of showing why we get these large igneous provinces as the head of a rising mantle plume at the beginning of its history. Talked about how they happen very fast. Oh, and now we're this is one of my favorite journals. It's called Elements. You get it with a $25 membership of the Geochemical Society, and they put them out 4 times a year. These special issues that give you very overviews of big things. I highly recommend it. Let me know if you want to find out how to join. I want to talk about our lip. So this is the Columbia River lip this is Washington State, this is Oregon, this is Idaho, California, Nevada, Utah, Wyoming. So what you see here this is the lip, the Columbia River flood basalts. Remember, we use flood basalts as a name for a synonym for lip, large igneous province. And this is 15 to 16 million years. Now, it is clearly related to the Yellowstone hotspot because the Yellowstone hotspot, which is basically igneous activity, hotspot volcanism going on today, is here, right? And so these other volcanic centers have been dated, and they go back. You can track this back to about 16 million years, which is when it was here. Now, does somebody want to say from this which way the North American plate is going? Can you guys look at this and go, oh, it must be moving in the X direction? Anybody? Bueller?
Southwest.
Southwest. Everybody see that? So the hotspot's here, and this must have been over the hotspot, some part of it. I don't know where. And then it was here at 16, here at 14. This is probably not the migration of the mantle plume. This is probably the motion of the North American plate over it. And you're going, how does he know that? Well, let's take a look. This is what the absolute plate motions are thought to be from Grip and Gordon. And you see, just as we expected, that the North American plate is moving to the southwest. So that's consistent with what we think about absolute plate motions. And, if you ever get a chance to go up there and take a look at that stuff, I encourage you. All right, so let's talk a little bit more about the Columbia River flood basalt, North America's best lip. We've got some other lips, but they're older. This one is well preserved. And there's, if we were taking this course at Washington State there and somewhere in this part of Washington, you'd be learning all about these sequences. And now these are the the accumulation rate, which could be the eruption rate, cubic kilometers per millions of years, going from 17 million years ago to about 6 million years ago. So there's three great sequences, actually four. There's the Imnaha, the Grande Ronde, the Wanapum, and the Saddle Mountains. And you can see the Saddle Mountains is all of this sort of very low volume and just keeps on putting it out a little bit, dribs and drabs, for a very long period of time. But the big outpouring, as we said, very quickly, the Grande Ronde, is between about, 16 and a half and 14 and a half million years ago. A little bit less in the earlier Imnaha, a little bit less in the later Wanapum. This is the huge outpouring of basalt that made the Columbia River basalt lip. So here is the hotspot track. This is called the Snake River Plain. This is a topography map, and what you can see is here we've got all kinds of structure in the basement, and Yellowstone is here, and the hotspot track starts over here with the Columbia River flood basalt and goes like that. And basically, where you are on the Snake River Plain because, as you get closer to Yellowstone, the igneous rocks, these volcanic rocks get younger, and as they're farther away. Yes, Clint.
This is fun and memorable to teach to introductory students with a big piece of cardboard labeled Idaho and a blowtorch.
Yeah. Well, anything with a blowtorch is going to be memorable for undergraduates. So I highly encourage you, and you may want to wear a helmet so that your hair doesn't catch on fire.
We went out to the parking garage.
Oh, okay. All right. There's Old Faithful Geyser in Yellowstone National Park. Highly recommended. If you haven't been there to see it, it's really one of the natural wonders of the United States. It erupts every 35 to 120 minutes for 1.5 to 5 minutes, and it will spew hot water up from 90 to 184 feet. So this is not a volcanic eruption, but clearly something is driving this, right? If you think about the mechanics, how do you make a geyser? It's actually a very interesting scientific problem. All right, so now let's zoom in on Yellowstone. So this is Yellowstone National Park shown here on this thing. For some reason, nearly all of Yellowstone is in the northwest corner of Wyoming, but for some reason there's a little bit in Idaho and there's a little bit in Montana. Don't ask me why. But what you can see is here is the Yellowstone caldera, and here is the history of big Yellowstone eruptions from 2.2 million years ago to 1.2 million years ago to 0.6 million years ago. So these are, this is 2,500 cubic kilometers. This is 280 cubic kilometers. This is 1,000. Now, the Mount St. Helens eruption in 1980 was a pretty spectacular eruption, but it only put out 1 or 2 cubic kilometers. So we're talking about things that are 2 or even 3 orders of magnitude putting out more material. It's we're kind of happy it doesn't happen while we're still around. Now, one of the things that's interesting about Yellowstone is we've been talking about these large igneous provinces and mantle plumes producing basalt, but what's being produced in Yellowstone is rhyolite. These are rhyolites. These are very felsic rocks, high silica, very different than basalts. Why? Well, here's the way that scientists see it now. So here we're looking at a cartoon going down to 75 kilometers deep in the crust, actually into the upper mantle, right? Because the crust is only about 40 kilometers thick. So this is the way that the people that work on this see it. I want to draw your attention to where the earthquakes are. So does anybody know why the earthquakes are all up here and not down here? Anybody? Come on. You guys know. Come on. Don't be
We already
shy.
talked about it.
Don't be shy. You guys are being shy. I don't like you guys. Why are you being shy? You know why there's no earthquakes down there, right? Right? It's because it's too hot, right? So this is all very hot. This is where you can have brittle deformation. So that's where the earthquakes are. It's only shallow earthquakes, and then down here, the deformation here is all going to be ductile. So hot, right? And so the idea is the mantle plume is pumping out basaltic magma that rises, interacts with the crust, which is continental crust, and partially melts it, so that you get this, a lot of rhyolite magma. Rhyolite magma is less dense than basaltic magma, so you get these layered systems. And so every once in a while, it erupts. There's earthquakes. You'll see in social media earthquakes swarm in Yellowstone, and obviously the geologists are interested because it could be an expression of magma moving up in the crust that could erupt, but generally it hasn't been. But that doesn't mean it can't happen in the future. All right. And we've already talked about this age progression. We don't have to talk about that anymore. Let's talk about the largest continental lip on the planet. This is the Siberian traps. These are flood basalts that erupted 252 million years ago. And that may be a time that triggers a bell in your memory. That is very close to the Permo-Triassic extinction. The end Cretaceous extinction gets all of the media because it killed the dinosaurs. But in fact, in terms of the number of genus that were killed, wiped out, the Permo-Triassic was a bigger extinction event. And whereas there's general acceptance that the end Cretaceous extinction was caused by a large meteorite, the dominant scientific opinion is that it was environmental change caused by the Siberian traps that caused the Permo-Triassic extinction. So this is way up there in northern Russia. This is the area that's shown over here. This is the area of exposure. Then you've got one of the great petroleum basins of Russia is related to this, the extension associated with this lip and the substance, and of course the thermal effects of a large igneous province, if there is organic matter, is going to cook it. So this West Siberian basin is, I don't know what percentage of Russian oil production comes from there, but a significant part. Now, another very famous one is called the Emishan Lip in southwest China, down here. This region is very deformed, and so you sort of only see pieces of this thing coming up. But this is also late Permian. This is not quite at the Permo-Triassic boundary, and it's 250,000 square kilometers as opposed to the Siberian trap, which is more than 2 million. But you can see here's the central Emishan lip. Here's the eastern Emishan lip, and this is outside of the Emishan lip. And you can see here this tremendous thickness of basalts here it's called the inner zone over here. And then the eastern large igneous province, much thinner, sort of thinning away. And this was a marine environment, so a lot of these basalts were submarine. So that's if we were teaching this course in China, you'd be learning all about the Emishan lips. Now the Deccan Traps is in India, and a very famous. So traps, it's like, what do you mean traps? Well, that's an old word for flood basalt. So when you see the word traps, think flood basalt. So this is well dated to be about 66 million years. And yes, Clint.
Right, and it comes from the Swedish word for staircase, because Swedish is different, but they look like staircases. It's like layer, 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 and they have them in Sweden or something, and that's why. That's why it's called that.
Yeah, maybe the Oslo Graben or it may have some of these things. But so this is darn. So there it is. And it's thought that it started down here, this this ridge here. I can't pronounce that name, but this is Chagos, and that's the Maldives. And then over here, we're in the Seychelles Mascarene Plateau. So it's thought to have happened down here, and then these things split off. And some people think that it was this lip that caused the Cretaceous Tertiary extinction event, not the meteorite impact. But I would say that's a minority of geologists. And then one that's going on today is this Afar hotspot. So here in Ethiopia, in Northeast Africa, we've got the Red Sea, the Gulf of Aden, and the East African Rift coming in here, which we'll talk about later. And here we've got lots of igneous activity ongoing. There was a large igneous province that was developed in Ethiopia and Yemen on the other side at about 30 million years, and now it's sort of lots of igneous activity just in this focus region in what's called the Donegal Depression. So that's a good example of an active mantle plume on the continents. All right, so we've got fixed location of mantle plumes is quite controversial for the Hawaii Emperor hotspot chain. So this is the chain we talked about, the black dots with their ages. And some of the paleomagnetic people have said, well, it looks to us like the hotspot track is moving. But you can see one of the problems is this requires some understanding about longitude, and paleomag is notoriously bad at giving you reliable longitudinal fixes. So I view this with some skepticism. All right, now this is Iceland over here, where the mantle hotspot is there.
Just going back to that Hawaii thing, I understand because there's four of them, Louisville or one of the other two, that all switch directions at about the same time. I still really struggle with, that's a huge plate. It's got tremendous momentum. What could cause a change in directions? I just can't even imagine what would happen that would cause a rapid change in direction.
Well, one of the key themes in plate tectonics, dynamics, right? We talked about the difference between dynamics and kinetics, and we've been mostly talking about kinetics. We really haven't talked about what drives the plate, what makes the plates move yet, and we will. But to spoiler alert, the plates are mostly driven by the sinking of lithosphere in subduction zones. So if you've got a change in plate motion like that, a major one, it implies that there is a new subduction zone that was created that started tugging on the plate at about that time.
Thank you.
And we'll talk more about this because as I said, it one of the things that students struggle with is these deeply embedded ideas about big mantle convection cells driving the plates. And you've seen that so many times in such an early stage that it's very hard to erase that from your memory banks. But that is my particular mission on this planet. I've been sent here by the Plate Tectonics Central to correct this misapprehension among Earthlings. And I'm failing so far, so I'll probably be recalled. All right, now Iceland is here. And so this is the trend that they've got. And And so it's like, okay, it looks like the hotspot started about here at 70 million years ago. Oh, maybe 100, 110. Oh, okay, so it's like that. And it's here now. So that predicts that there must be some evidence of this hotspot underneath the Greenland ice, doesn't it? So what will we find when the ice melts? So here is a magnetic anomaly map. So there is Iceland, right? So do you see evidence in the magnetics for the Iceland hotspot track in the magnetics? And this is just sort of a brain teaser for you. There is no right answer, but it makes you kind of go, gee, I wish I understood magnetics more. A useful thing. All right, so recall the apparent polar wander path for Gondwana, right? So this is the, in the sort of the end of the Precambrian, Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous. Today, down here, right? That's Antarctica. So, and we've already said this is not the magnetic pole moving that much. This is the continents moving. So we can put the continents together again to get a single path, right? South America next to Africa, next to Antarctica, next to India, next to Australia. And we've shown this over and over again. But what if the rotation poles actually move, right? We've talked about apparent polar wander. That's apparent polar wander, APW. Is true polar wander possible? And the answer is yes, right? So imagine that Earth's rotation axis, which is right now here, switch to there. What would the magnetic north do? Would it stay here or would it switch over to here? And it's generally assumed that what will happen is that the magnetic pole will also go there. So this is an area of quite controversial. It's useful for you to know that the word apparent polar wander is to be contrasted with the word term true polar wander, and the true polar wander could happen if the moment of inertia for a planet shifts. And this would only happen if there was a redistribution of Earth's mass, maybe due to drifting continents or the development of new or the buildup and disappearance of glaciers. That's simply to not to confuse you more than absolutely necessary, but simply to alert you to the fact that there is a thing called true polar wander. And some people, these authors have suggested that as much as 30 degrees of true polar wander is thought to have occurred over the past 200 million years. This is their confusing diagram, not mine. Now, one thing I want to talk about is this Cretaceous superplume. So we've already talked about the magnetic quiet period. That's shown here between these two dashed lines. This was a time when there were no reversals, right? There were reversals before it, the M series we've talked about, and then there have been reversals after it, which have been increasing pretty much through the Cenozoic. Okay, but a lot of other things, interesting things happen in here. For example, the production of oceanic crust doubled during this time period. Another thing that happened is an awful lot of oil resources were created at this time because black shales were preferentially deposited during this interval. Sea level was high. The temperature was also high. All of this happened during this time, and it's led to people talking about a mid-Cretaceous superplume. And with that, I'll switch over to Clint.
Is this why Siberia is expected to be the next location of the pole? And you mean the magnetic North Pole? Yes.
Yeah. No, this is not a true polar wander. This is just the sort of the way the magnetic pole sort of wanders around. Siberia is not that far away from the North Pole. right now the magnetic North Pole is in northern Canada, and it sort of wander over to northern Siberia. But that's more just sort of small scale expected variations rather than a change in the Earth's rotation. True polar wander is really mostly about Earth's rotation pole changing and then the magnetic pole changing with it catastrophically. All right, so we're going to go back to these plate motion kinematic models, and let's talk more in detail how we measure plate motions. And these are the plate motion kinematic models. So direct measurements of relative plate motions have led to the development of two kinds of plate motion kinematic models, which we can divide into geologic and instantaneous. So geologic are based on magnetic anomalies, transform orientations, earthquake slip vectors, the sorts of things that we use to work out the three ways of getting relative plate motions. And these rates are determined for the last 3 million years or so, not very far back. And these are in two kinds of models. The first one was called Nouvelle 1, which evolved into Nouvelle 1A. So Nouvelle is new velocity model. And Morval is more recent. Morval is mid-ocean ridge velocity model. These are based on these things. Now the instantaneous plate motion kinematic models include Revel and GeoDevel. These are determinations of nearly instantaneous plate motions from space geodesy, such as GPS, but also including a few other systems. And these have only been done for the last few decades. This isn't an absolute determination of motion, but it can easily be converted into relative plate motions to compare with Nouvelle 1A. So, okay, so let's just say you're a skeptic of all this plate tectonic nonsense. So we could come up with these models to show you why you're wrong, but you might go, oh, all this magnetic stuff and earthquake slip vectors, that doesn't convince me. So it's like, okay, what if we use GPS and we can only measure these motions for the last 2 or 3 decades because that's only as long as we've had the technology. But what if they agree? Would you be convinced? And you'd probably say, sure. So how do plate motion vectors determined for a few million years, geologic ones, compare with those determined for a few decades, instantaneous? And here we have a map that purports to show the plate kinematic models using Nouvelle 1A, that's geologic model. Those are the yellow arrows. And then the ones with GPS, which is Revel, which are the purple arrows. And so you can look around at these, and what I see is they agree pretty well. And they agree especially well when the rates are high, like the Pacific plate agrees very well. And when the rates are lower, like you have maybe in South America or Africa, they don't agree quite as well. But for the most part, you would have to say that this completely independent method of determining plate motions agrees with the geologic one. We can quibble, but for the most part, it doesn't refute it. It supports it. All right. Now, recall the relationship between the angular and the absolute velocities. So angular velocities are in degrees per millions of years, and the absolute is in kilometers per millions of years. These are two different ways of measuring velocity, and that the convergence to divergence velocity of a plate A relative to plate B is A sub A V sub B, and this indicates velocity at any point on a plate B relative to A across that boundary, according to that trigonometric relationship. This A sub A big V sub B in kilometers per million years is equal to the radius of the Earth times the sine of the angular distance from the Euler pole times the angular relative velocity, right? So for this plate motion, everything is moving at the same angular plate velocity, but the absolute varies as a function of the latitude, the sine of the latitude, right? So let's look at some comparisons. These are spreading rate and transform azimuths for the Australia-Antarctic plate boundary, right? So Australia and Antarctica are moving apart. There's a mid-ocean ridge between them. Oops. And over here on the left, we're looking at the rate, and over here we're looking at the azimuth, clockwise from north, right? That would be due north. This would be, sort of off in the northeast. And what we can see is the curve for Ravel. In the dashed line, the curve for Nouvelle. These are both geological rates. And Ravel is instantaneous, Nouvelle is geologic. I apologize. And so they agree very nicely. They couldn't agree better. Now the azimuths are also predicted, and you can see they also agree very well. So if we go plate boundary by plate boundary, for the most part, we see a remarkably good agreement between the geologic and the instantaneous ways of measuring plate motions, rates, and azimuths. Any questions about that? There might be a question, seeing if you remember the difference between geologic and instantaneous plate motion kinematic indicators on the midterm. All right, so Morval and NNR Morval 56 are geologic. This is, rather like Nouvelle, right? So we don't need to go into too much detail, but it's here. And as you know, all of these PowerPoints are loaded in e-learning, and this will be available to look at as well. GeoDevel is instantaneous, and it's sort of like Revel. And these are space geodetic observations from 4 techniques. Yes, GPS, but BLBI is very long baseline interferometry. SLR is satellite laser ranging, and DORIS is a French Doppler orbitography and radio positioning integrated by satellite. So this, yes, Clint.
I forget, do you have a diagram of the 2 satellites chasing each other?
I do not. That's not what we're talking about here. That is actually GRACE, which is a gravity measuring. This is not, we're not measuring gravity here. We could and probably should have an entire course on how we study the Earth from space, but that would require some effort on my part to put it together. But what you're talking about is measuring gravity from space, which has been a huge boon to studying the Earth, but we're not talking about that here. This is GPS, etc. All right, so I asked my friend and very accomplished colleague Tim Dixon. This is a while back. I said, I found the new space geodetic model. They trumpet that their results are different than Ravel, but you'll have to explain whether there are any significant differences or if it is a tempest in a teapot, as experts are wont to do. I also found 2 models to replace Nouvelle 1A Morval and NNR Morval 56. Now that's a mouthful. And I asked him, do you think GeoDevel is an improvement over Revel? And the reason I asked him that is he and his graduate student developed Revel, and that Morval and MNNR Morval 56 are improvements over Nouvelle 1A. Thanks, Bob. And he wrote back, I don't think the differences are all that significant, but of course the same thing could be said about Rouvel versus Nouvelle. One problem with Morville is that the mix of present-day GPS earthquake and 1 million-year-old data. GeoDevil is pure geodesy, so it's more directly comparable to Revel. There are differences of 2 to 5%, so anyway, that's sort of, he helped me sort of get my brain around this extremely complex science by telling me, don't worry about it, Bob. It's not too much different. All right, so now we get into the chapter on finite plate motions. And to remind you, Euler's theorem tells us that any displacement on the surface of the globe can be modeled as a rotation on some axis. And the combination of axis and angle is called a finite rotation. So, thinking about finite plate motions for 3 simple plates, what do the Euler poles do? So here we've got 3 plates, which means we have to have 3 Euler poles. One for the rotation of A relative to C, that's angular rotation, right? One for the rotation of B relative to C, then one for the rotation of B relative to A, right? So plate A, we're going to fix plate A, and therefore the pole of AC and the pole BA are also fixed. So only the pole between B and C is going to move. And we can see that here, right? Because B and C are changing size. So there's one pole, that's the original pole, and that's the new pole there, that dashed line. So the transforms around the poles are fixed between these two, but those around the BC poles will shift azimuth as the pole shifts. So here we see it. Now we switched over to 2 plates, B and A, and remember here's the pole between B and A, and we have this part of the transform is defining a small circle around the pole of rotation. And then let's say we move the pole from here up to here, then that small circle is, and that transform is still there, but it's going to change its the radius of that small circle. So the early poles are shown by this trace, which is now a fracture zone, right, FC. And the new transform is going to be shown by this segment. So if you can figure out the age of the crust, then you can determine the age of when that motion of that pole changed, right? And that's what Menard and Atwater did in their study of the Northeast Pacific fracture zones. They found evidence that they found changing Euler poles between the Pacific plate and the Farallon plate, which no longer exists off of California, but is still, we call that the Cocos Plate now, or the Rivera plate up here, or the Juan de Fuca plate up here. That's the remnants of it. And these are the segments of their fracture zones. Now, you may find this unconvincing. I'm not terribly impressed. Kind of looks like a linear Rorschach test to me, but I thought I'd bring it to your attention that that's what they did. Now, one of the things you can say is you can put modern earthquakes on an Australia-Antarctic ridge and superimpose this on a reconstructed Australia-Antarctic plate margin. So here we've got Australia and Antarctica put back together as they were before they broke up. And then we're just showing where the present earthquakes are, which, as you know, they mark where the plate boundary is. And you can see that it looks like there's been no significant change in the pole of rotation of Australia relative to Antarctica, because these earthquakes basically mark where that rift would have started, as well as even though it's modern earthquakes. So it demonstrates little change of the Antarctic and Australia Euler pole over the last 60 million years of plate separation. Now, there's a software for the interactive visualization of plate tectonics called GP plates or G plates. And this is lets you build your own plate tectonic reconstructions. It runs on Windows, Linux, and Mac OS. It has an online user manual, free software, and it's very powerful if you want to learn how to use it. Right? Just go there and you can download it, play with it. Let's look at a little video. So this is done in G plates. We're looking at Australia down there, approaching Asia, and that we're back in the Cretaceous, and then that rifting between Australia and Antarctica starts, and then everything changes. Right, that's where we are today. We can watch it again. Kind of, everybody loves a new video. Watch a video. There is no sound, so if you're not getting sound, well, you're hearing me. I could sing along, but probably you don't want me to. There goes India.
Splat.
All right, now let's look at some more animations, G-plate animations. This is of North America, and they're each going to show the same time period, 200 million years ago to the present. In the first one, all of the plates are going to move. In the second one, we're going to hold North America fixed and look at the northern hemisphere. In the third animation, we're going to hold North America fixed and look at the southern hemisphere. And I'll ask you for each of them, is this absolute or relative plate motion? So here we go, the first one, right? 200 million years ago. Wait a minute, did I there we go. Go. So you're creating some terrains there in North America. So is that absolute or relative plate motion? Anybody? You want to watch again? What do you guys think? Absolute or plate or relative plate motion are we seeing?
Seems like it's absolute to me, is because the poles aren't changing.
Well, you don't see the poles, but I agree it's absolute because you're seeing all of the plates moving, right? And relative plate motion, that's you got to hold something fixed. So I think this is relative plate motion. Now let's hold North America fixed and see what's going on.
So you're saying it's relative, or?
No, this one is
okay. When you hold North America. Okay.
This one is absolute plate motion. So you see what Africa's doing? Even though there's a spreading ridge between North America and Africa, Africa's moving to the west, right? And that's because, this spreading ridge lets this part move faster to the west than this part. And actually it changes the direction. This I agree is absolute plate motion. Now let's hold North America fixed and see. This is the same scene, all we're doing is doing different things. In this case, all we're doing is holding North America fixed and letting everything move relative to North America.
I can see the map at 199. There we go. Hot dog. Look at that. Damn Greenland. Trying to escape our cult.
Okay, absolute or relative motion?
Relative.
Yes, because we're holding North America fixed, right? Now
Yes.
let's hold North America fixed and see what's going on in the southern hemisphere. Okay, and that's what you can do with G plates if you and it's not real hard to learn. We can, anybody wants to learn about this stuff, we can arrange for a little tutoring for you. Okay, yeah. All right, so in the last part of this lecture, we're going to talk about the stability of triple junctions because we have a few questions about that on the midterm. All right, so let's talk first about unstable plate boundaries. So this is New Zealand, North Island, South Island, Pacific Plate, Australian Plate. The Pacific Plate is being subducted beneath the Australian Plate in the north, and the Australian Plate is being subducted beneath the Pacific Plate in the south. And in between, you have transformed. And because of these two convergent margins, this strike-slip fault system is changing with time. It's getting longer. So we see this as an unstable plate boundary. So what we can imagine is this is in the north, this is in the south. In the south, X is subducting beneath Y. In the north, Y is subducting beneath X. And as a result, they're migrating. This west-facing subduction zone is migrating to the west. This east-facing subduction zone is migrating to the east, and a strike-slip fault develops between them. And here we can see that applied to New Zealand and the Alpine Fault. Okay? So this is just the idea of an unstable plate boundary. You can't expect to come back in 10 million years and see the same thing. It's going to have evolved, changed. So let's apply this to triple junctions, right? What is a triple junction? So a triple junction is the point where the boundaries of three tectonic plates meet. At the triple junction, each of the three boundaries will be one of three types: a spreading ridge, R, a trench or subconvergent plate margin, a T, or a transform, F. So sometimes we get confused. T is trench and F is transform, but that's what it is, RTF. So triple junctions can be described according to the types of plate margin that meet at them. So for example, FFT, RRR, right? That what I wrote there, fault, trench, that should be transform, trench. I apologize. Of the 10 possible types of triple junctions, only a few are stable. And stable in this context means that the geometrical configuration of the triple junction will not change through geologic time. So the meeting of 4 or more plates is also theoretically possible, but these junctions are all unstable and will only exist instantaneously. So we're not going to worry about them. So how do we decide which triple junctions are stable and which are unstable? And the answer is we conduct a geometric analysis. So here is a geometric analysis of an RTF triple junction. So R, there's the spreading ridge. We show that with double lines, and we can show the spreading direction, right? This is the F, right? This is a strike slip fault, and we can see that's a right lateral strike slip fault system, transform. This is obviously a transform. And then this is the trench or the convergent margin, and these little teeth are on the overriding plate. So A is subducting beneath B, and the relative plate motions are there. So let's conduct a geometric analysis of whether this triple junction is stable or not. So the way we do this is break it down into pieces. So here we've got the geometric analysis of this convergent margin. It's oriented like that. A is being subducted beneath B. So the way we would show that plate motion vector is like this. A is moving in this direction relative to B, right? B is relatively fixed. A is moving that way. So the dashed line AB marks the possible locations of associated triple junctions, called the velocity line. This is called the velocity line. It's confusing because this is actually showing the velocity, but for some reason, they call this the velocity line. So B must lie on AB because there's no motion of B relative to the trench. Does everybody see that? All right, let's do a transform. So B is moving to the southeast relative to C, right? So that would look like that. B is moving to the southeast relative to C, and that motion is occurring along this BC velocity line. Okay, everybody see that that's the way you would portray that? And your book goes through this too. I'm just going over what's in the book. And then this is the spreading ridge velocity analysis. So C and A are moving apart in orthogonal to the trench. We would show it like that. So this would be capturing the full rate of spreading, whereas each of these arrows is a half rate, the way we've been discussing it earlier. All right. So put it together. So here we're putting all of these three geometric analyses for each of the junctions together. There is the motion of A relative to C, right? A relative to C is perpendicular to this velocity line AC. And B and C and B and A are both moving along this trend. One of them is moving, A is moving relative to B like that, and B is moving relative to C like that. So you end up with this kind of a thing. And the rule is that will be very useful on the midterm is if the three velocity lines, which are dashed between the three plates, all intersect in one place, then the triple junction is stable. It may migrate up and down the trench transform fault, but it will continue to exist looking like this. By this analysis, this triple junction is stable. Here is an example of an unstable ridge trench fault transform triple junction. So still three plates, still a spreading center, a trench, and a transform. But when we do the geometric analysis, the velocity lines do not intersect in a single spot. So by this analysis, this triple junction is unstable. It will disappear. It's not clear what it's going to become, but it will not be recognizable in significant time in the future. Now here's another one. These are the positions the plates would reach if not subducted, right? So here's Here we got a convergent plate margin subducting B beneath A and B beneath C. So if we do the analysis there, these don't intersect in a single place. These velocity lines do not intersect in a single place. On the other hand, this one is slightly different, right? The main difference is the direction of C, right? This one looks like this. And it does intersect at a single point. This triple junction is stable. Okay? So I invite you to spend more time on your book because there's 3 or 4 questions in there. And these, are a whole bunch of different kinds of triple junctions that are stable and unstable. And you can see that. These are the representations of them. That's a ridge, 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 trench, 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 fault, 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 So I don't have to go over each of these, but we'll look at some examples of triple junctions that are stable and unstable. So if we look at the evolution of the San Andreas Fault. Yes, John.
So it doesn't depend on what type of triple junction it is. Any type of triple junction could be stable. Any type of triple junction could be unstable.
I think that's true. I honestly can't say that I'm confident it's true, but as long as it satisfies this rule of the velocity lines meeting at a point, it is stable according to geometric analysis.
Okay.
Let's see if we can find in this list. So here's a ridge, 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 which is stable. Here's a trench, 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 stable. This is a fault, fault, fault one. It's unstable. Yeah, these are a lot of stable ones, but it looks like if it's a fault, 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 it is inherently unstable. I hadn't thought about that before. Good question. All right, so let's take look at some of this analysis. So here we're going to be talking about the San Andreas Fault of California quite a bit. So it's kind of interesting. Here's cutting through California, and it goes from a sort of a interesting ridge transform system down in the Gulf of California, and then it ends up up here with a spreading ridge and this Juan de Fuca plate being subducted beneath Oregon, Washington, and northernmost California. So how did this system evolve? So this is the geometric analysis that Tanya Atwater put together. And when I was a undergraduate, just finishing up at UC Davis, this really caught my eye because this happened at the Scripps Institution of Oceanography by a graduate student, not a professor. And I was just smitten with these ideas. So here we're looking at the sort of the plate configuration at 40 million years ago. What we've got here is the North American plate. There's a subduction zone. There's lots of evidence for this in the Sierra Nevada batholith and Mesozoic igneous rocks of Western North America. And it's subducting the Farallon plate. And the Farallon plate is separated from the Pacific plate by a spreading ridge. And we've talked about some of these fracture zones. This is the Mendocino fracture zone. This is the Murray. We talked about that a little bit when we were talking about this work that Tanya Atwater did with Henry Menard. There's the Mendocino, and there's some other ones here. Those are the fracture zones that they used. So that's going back quite a bit farther back in time than we're dealing with here. Okay. So today the Pacific Plate is not only right offshore of California, a significant part of California is on the Pacific Plate, including Los Angeles, goes right through San Francisco and all of Baja California. So this plate boundary has evolved quite a bit since first this ridge was subducted. So this is the analysis. So the ridge begins to be subducted around 20 million years ago, which you will immediately recognize as early Miocene time. And this is the velocity analysis for this boundary. This is a triple junction, right? This is a F, F, T triple junction, right? And each of these has convergence. Now, I wish they were using dashed lines, which they don't here. But this one is stable. That point doesn't change. But this one is quite a bit different. This one is unstable, and it propagates to the south. So that the San Andreas Fault started about 20 million years ago. It was very short, and because this southern triple junction was unstable, it migrated southward with time. And today it looks something like this. Okay, that's the power of this analysis. Was it explained how this really strange tectonic situation came to be just in the last maybe 25 million years. So let's watch a 4-minute video that we put together